everyone. Welcome. Super excited to see all these folks out here. So welcome to, this is our first in-person department seminar since February of 2020. So I think that deserves a round of applause. And I have been hoping to get Stephen Godfrey here for about 3 years, but the pandemic intervened, and now I'm super excited that we could make this happen. For those of you who don't know, the geology department hosts department seminars. What do you think, Brett? Maybe 3 or 4 times each semester. We have external speakers come in from a variety of different universities and museums and tell us about their research. This is the first time we've ever had anyone speak about Megalodon. So I'm like really excited for this. So to give you a little of background on our speaker, so Stephen Godfrey is now at the Calvert Marine Museum. He's been there for about 23 years. He did his undergraduate degree in biology at Bishop's University, which is in Quebec. He's a fellow Canadian. And then he went and did his PhD in Curator of Paleontology at McGill University. So as a lot of you know, paleontology is one of those truly interdisciplinary fields where most of us who study it have multiple degrees that span geology, biology, and sometimes even other data science and various other fields as well. Today, we are super excited to welcome Stephen. I'm going to go ahead. Hey, Kayla, come on in. The water's warm. I'm going to ask folks to give Stephen your attention for about maybe 45 minutes.
Yeah, more like a half an hour, 35 minutes.
Good. And then we're going to have plenty of time for questions. So while Stephen is presenting, I want you guys actively brainstorming about questions. This is your chance to ask, Elizabeth, any questions you've ever had about Megalodon, about fossil sharks in general. Just so that you all know, Stephen works, because he's really focused on the Calvert Cliffs, which is an amazing set of fossil localities in Maryland. He works on a variety of things. I knew his work initially on dolphins and marine mammals, but then of course on sharks as well. So do me a favor and let's give Stephen a round of applause. Thank you so much for joining us.
Thank you very much, Rowan and Brent, for the invitation. It's good to be here. Yes, I've been looking forward to this for a long time, so it's nice to have you in my clutches. So yeah, without any further ado, so what I've noticed over the years is that restorations of Megalodon on the internet just get larger and larger and larger. And of course, back in 2013, there was the Discovery Channel mockumentary claiming or reporting that Megalodon was still alive. There are movies about Megalodon. I have not seen this movie, but I love this poster because look at so Megalodon versus giant octopus. Look closely at the ornamentation on the back of the octopus. Now, Rowan, you should recognize this. When I first saw it, it was like, wait a minute, I know what that is. So the artist who created this actually cut the front half of a ceratopsian dinosaur skull and slapped it on the back of the octopus. Here's the beak, there's the nasal opening, there's the nasal horn core, the eye, and the orbital horn core. Vertebrates rule.
Hey.
And of course, the Meg movie, I kind of really enjoyed it. I found myself laughing out loud during parts of the movie that I don't think were supposed to be funny, but it was just like so over the top that I just, yeah, I loved watching it. Now, back in 2017, I had the pleasure of working with a French film company out of Paris, and they were doing a documentary. So they were interested in the science of Megalodon. And so it was heartening to work with them. And they commissioned some high-end graphics and animations for the documentary. And this was their restoration, their artistic restoration of Megalodon, of about a 60-foot-long Megalodon. Now, if the truth be known, we don't actually know what Megalodon looked like. That's because we only have teeth and a few specimens that have associated vertebrae. So we don't even know the vertebral count in their backbone. However, Megalodon is a lamniform shark, which includes great whites and makos. And so this is not an unreasonable restoration of Megalodon, okay? As part of that same documentary, I got to go to the Atacama Desert in Peru, the driest place on earth, where there's just like no vegetation whatsoever. And in this small village, Okukaje, next to the Atacama, they had this rather nice restoration of the head of Megalodon, and I would love to have something like this at our Marine Museum. So in the fossil record, here's the sort of classic Earth timeline spiral, beginning with the formation of the Earth 4.5 billion years ago. Megalodon had a pretty good run from about 22 million years ago, and we think they became extinct about 3.5 million years ago. So for almost 20 million years, Megalodon was the top marine predator on Earth. Now, if we look more broadly at the group of sharks that Megalodon belonged to the lineage, their story really starts about 60 million years ago with a shark known as Otodus obliquus. This one down here. It was about the size of a modern great white shark. And we think that this is what we would refer to as an anagenetic lineage. So that simply means that one species evolves gradually into another, and there isn't radiation or branching in terms of speciation. There's not a whole host of different kinds of sharks living at the same time, one that evolved from another. This is one species simply gave rise to another, and the morphology changed through time without that lineage branching and giving rise to lots of different kinds of sharks. So we start 60 million years ago with this 20-foot long shark, and it culminates in Megalodon, which is over 60 feet long. So here's a representative sample of the teeth, lower teeth of these different species of sharks. And here's the 60 million year old Otodus obliquus. And this kind of shark tooth is analogous to a fork. The cutting edge right here is smooth. It doesn't have serrations. And it's relatively narrow at the base. And so this tooth is really effective at puncturing the bodies of slippery prey and swallowing them whole. It's not very efficient as a cutting tooth. However, the single most important innovation, evolutionary novelty that occurred within this lineage was the acquisition of a denticulate or a serrated cutting edge on the tooth. And that occurred here about 45 million years ago with this animal known as Otodus auriculatus. So the serrated edge tooth then immediately transforms that tooth into a steak knife, into a cutting implement. And the serrations are retained through the balance, the remainder of the lineage that eventually culminated in Megalodon. You'll notice also that these little cusplets at the base on the shoulder of the tooth then also are reduced until they disappear in Megalodon. So what's interesting, I'm just going to go back. Like a second. What's interesting about the last, so these two species here, Chubatensis, which is the ancestor of Megalodon, both of these species, or chronomorphs, occur along Calvert cliffs. We have both of them preserved in the cliffs. And it has long been known by collectors that you find a preponderance of Chubatensis form teeth in the older sediments along the cliffs. And as you ascend into progressively younger strata, most of the teeth that you find are of Megalodon. So this is a lovely evolutionary transformation. And we wanted to see if we could sort of characterize that empirically, document it more thoroughly. And so we were able to accumulate a sample of 250 teeth from along Calvert Cliffs, Langley Bluff, Chancellor's Point, and this place called Pope's Creek. So all in southern Maryland. The next tooth that I'm going to show you is from Pope's Creek. And these 250 teeth are all Miocene in age. Okay, so they range in age from about 8 million years to about 22 million years. Okay, so, but the next tooth I'm going to show you is actually from Eocene strata, from strata that's like 50 million years old. And it underlies, there's a disconformity, there's an unconformity, underlies the Miocene age sediments that have been found there. So this tooth is this first member of this lineage that gave rise to Megalodon, the auriculatus, that first evolved the serrations along the cutting edge of the tooth. So you notice how bold the serrations are. They're not even, they're cut very uneven, and it's a 50 million year old tooth. So if we jump 30 million years to the Miocene age sediments, this is the type of tooth that we find. It's the tubatensis form with the small cusp on the side, on the shoulders of the tooth. The base of the tooth has become broader, and you'll notice that the serrations are very even. They're smaller, but very even. Here is another tooth that we coded as tubatensis, and you'll notice that the cusplets are really like vestigial. So there were quite a number of teeth that we struggled to place them either within the tubatensis form, were they that, or were they a Megalodon form? So in an evolutionary continuum, at some point, it becomes really difficult to decide, should I attribute this to the tubatensis shark or to the Megalodon shark? So this is the 15 million year old tooth, and even here, there's a slight hint of the sort of enlarged cusplet on the side of the base of the tooth, but here we coded this one as a Megalodon. And then finally, this tooth here, 14 million years old, obviously a Megalodon tooth, no hint of the cusplets remaining on the tooth. So here are the results of our study. And I just want to point out a few things to you. So the top numbers just represent the sample size for each of these bins. Okay. And then here, MA is, well, you would know your geologist, mega annum. So this is time along here, starting at 50 million years ago. So these are the auriculatus teeth, that first coarsely serrated tooth that I showed you. And then we jump, there's a hiatus here of about 30 million years. And then we're into the Miocene. So this is Eocene, this is Miocene. And these bins represent recognizable bends along Calvert Clifton in southern Maryland. So you'll notice that about between 20 and 18 million years ago, about 87% of the teeth are of the tubatensis form, have that cusplet at the base of the crown. And then over the next 10 million years, the proportions flip. Megalodon becomes increasingly more common. But what's amazing to me is that it took 10 million years for evolution to basically rid that lineage of that little tiny cusplet at the base of the crown of the tooth. What I don't think is happening here is that these actually represent two distinct species. I don't think they're sympatric species. That is, two separate species that are not reproducing, that live in the same area. I think this represents an evolutionary continuum, one polymorphic species. So this is like one population, and the genes within that population are just changing through time, developmentally. There might have been a change in the cascade of genes that were coding for that little cusplet, but it was reduced until it was essentially gone down here 8 million years. So there's only one tooth in that sample. So the tubatensis form may have hung on beyond that.
Well, it's hard to hear him once again.
So for the rest of the talk, or most of the rest of the talk, I'd like to show you fossils that tell an extra story. I love when fossils tell an extra story. The first story they tell is what they are. Okay. The extra story is sometimes they show that there's been some sort of interaction with some other animal, trophic interaction, and so predation. Now, most of the collectors that walk along the cliffs are hoping to find teeth of Megalodon. And we know that they were preying on whales and dolphins and seals and sea cows because from time to time, we find fossilized bones of those animals that have bite marks that were definitely made by Megalodon. And here's a good example. So this broken bone is actually a partial lower jaw from a baleen whale. You can see the arrow pointing at the lower jaw. And on average, baleen whales during the Miocene were much smaller than the large whales that we have living today. So this was actually a fairly good-sized Miocene whale. And this bone has multiple gouge marks on it from an overachieving Megalodon. And you can see here in this image where the edge of the tooth struck the bone, and then it raked the surface, the serrations, basically leaving a Megalodon calling card on that bone. Now, in this bone, there's no evidence of healing. Had this whale survived this encounter, there would have been like callus formation, like the tissue on the outside of the bone, the periosteum, would have responded to that injury, and new bone growth, like a callus formation, would have formed. And it would have remodeled that and basically done away with those serration marks. From this, though, we can't tell if this is evidence of active predation, the megalodon killed the whale, or was the whale already dead and it just scavenged the carcass. We can't tell from a fossil like this. The next bone that I'm going to show you is one of these blackened caudal vertebrae. It's called a peduncular vertebra, and they sit just in front of the tail fluke that propels the dolphin through the water. This is just a life restoration of one of the most common types of dolphins that we find along Calvert cliffs. The family Uranodelphinidae, just refers to their really long snout. So here's the bone, looking at the left side and then the right side, and kind of obliquely from the bottom looking up. Now, if this bone were a normal caudal vertebra from this kind of dolphin, you wouldn't have those deep gouges on both sides of the centrum. Okay? The only way that you can get deep gouges on a vertebra like this is if at some point in that dolphin's existence, that vertebra was deeply wedged between two adjacent megalodon teeth. And what's more, each one of those gouges represents a separate bite by megalodon. So it's as though megalodon is saying to this dolphin, "You are never going to get away from me." So we know by studying modern great white sharks that they will sometimes bite the caudal peduncle, the tail region of dolphins, to immobilize them, either cut the muscles tissue, or else more likely to sever the arteries and veins, and so the dolphin will bleed out. Because it's a lot easier to eat an animal that's already dead than you're just scavenging the carcass, as opposed to wrestling with a live animal. So we think that this then represents active predation. But this shows that the megalodon was chasing the dolphin and bit it repeatedly to immobilize it so it couldn't swim away. Because there'd be no reason for it to bite it so many times if it was already dead. And the other thing that's interesting is, this is something we learned from looking at living great whites. They will scavenge the carcasses of animals that are bigger than themselves. But for some reason, and I don't have an explanation for this, they won't scavenge the carcasses of animals that are smaller than themselves. They will, however, hunt and kill animals that are smaller than themselves and consume them. They're just kind of picky that way. And so if the same logic and feeding tactics were applied to Megalodon, then this would potentially show evidence of active predation on the part of Megalodon. It wasn't just a giant scavenger. Here's another really nifty fossil. It's a sperm whale tooth. Sperm whale, I don't know, 5 or 6 inches long. And you can see at the very top there is where the, oh, here, right here. You can see the crown of the tooth. So that's the enamel part of the tooth. Okay, and the rest of this is just the root of the tooth. Now it has this white chalky appearance because it's been coated with sublimed ammonium chloride. I don't know if you're familiar with that technique, but you heat up the ammonium chloride, which is a solid, over a Bunsen burner, and it sublimates. It turns into this white powder, and then you have a gentle compressed air that blows through it, and you can coat a fossil that's black or dark, and you wouldn't be able to see much of the detail if you're wanting to publish a paper on it. And so if you coat it with this sublimed ammonium chloride, the detail just really pops on the fossil. And so here, well, actually, the 1, 2, and 3 are 3 gouges that were made when a megalodon tooth or teeth bit this sperm whale tooth. So here you can see the evidence of the megalodon tooth. Again, the serrations that came down and sliced into the dentine of the tooth. Again, megalodon leaving evidence that it had some sort of trophic interaction with this sperm whale. So this is the first fossil that we have in the fossil record that shows an interaction between a megalodon and a sperm whale, between 2 macro predators. So it was like, megalodon and sperm whale, or sperm whale and megalodon. What's also interesting is that since this part of the tooth is embedded in the jaw, for the Megalodon tooth to mark this area, it would first have to cut through the bones of the jaw, either lower or upper. We can't tell if this is a lower or an upper tooth. So that to me implies a powerful bite on the part of the Megalodon to be able to cut through those bones first before the tooth then slices into the tooth of the sperm whale. So again, from this fossil, we can't tell if this is active predation or just scavenging. But we think we can make a stronger case for active predation, because if the sperm whale is already dead and floating at the surface, or it's on the bottom like a whale fall, there's not much reason for the Megalodon to come along and chew on its face, because there's not much return for the effort. There's not much flesh there. To me, this suggests an aggressive, antagonistic behavior by Megalodon to kill the sperm whale. Look, if Megalodon is chewing on your face, he's probably trying to kill you. We also think that we have fossils that show evidence of failed predation. So it's not that uncommon for great whites to attack seals or sea lions and for them to not kill their prey. Okay? And those animals then preserve in their bodies the scars of their encounter with the great white. So we think we have fossils that show the same thing. And I actually brought the fossils with me, and I'll show this to you in just a minute. So this is the place along Calvert where these two vertebrae were found, along with this relatively small Megalodon tooth. And they are lumbar or lower back vertebrae from the whale. And again, that's, you know, the approximate size of the whale to our Miocene skin diver, a scuba diver. So here's the first vertebra. It's here. And what's really nifty about this vertebra, so I'm just going to point out, so this is the neural spine that sticks up. You can feel like down your back. This hole, thank you. This hole right here is for the spinal cord that went down the back, the zygapophyses that articulate with the next vertebra, and then the transverse processes on either side that muscles would attach to. So this is the this is the back. This is the posterior face of the vertebra, and so this is what this end should look like. Okay, but this end like is seriously messed up. We'll come back to this in just a minute. We know that this animal was mature, was fully mature, because this piece, this tapping bone, which is called the epiphysis or epiphysis, epi means on top of, and physis refers to the length of the bone. So it's fused to the centrum of the vertebra, which means that this animal had stopped growing. Okay, the growth plate here is no longer active, and so the bone is no longer increasing in size. This end here, though, has two really interesting features. You'll notice that there's this deep concavity here. The trauma that this whale experienced was so severe that it disrupted the blood flow to the bone right here. Okay, bone is living tissue, and it has to receive nutrients. And so those were interrupted, and so the bone died. It became necrotic. And so osteoclasts, which are the cells that resorb bone, went to work, and they removed the dead bone from that area. But the osteocytes, the bones that form new bone, hadn't yet filled in this space. Okay, so the whale died sometime after the injury. It survived the attack by whatever. I know you know where I'm going with this, but what's also interesting about this is you'll notice that about half of the lower part of the vertebra was smashed away, was broken away. This we would refer to this as a compression fracture or a spall fracture. Now, when I first saw this vertebra, I wondered why this piece right here had not moved back up into place after the trauma, after the injury. Okay, yeah, you can go ahead and turn the light off, I guess. So this is, we CT scan this bone, and this is a sagittal section through the vertebrae. You can see the neural spine up top, the neural canal. This is the centrum. So this piece right here, this edge right here should actually be up here. So you can see that it was broken away, but not. But what's more, the back end of this piece, which used to sit right here, was forcefully jammed into the back part of the vertebra. It was pushed so hard into there that it couldn't close. So this bone down here called periosteal reaction, that's the proof that this whale survived this trauma and lived long enough for this new bone growth to form in here to keep this piece from returning to its original place. Just wondering if there's anything else I want to say. Okay. So this is the second vertebra. So these two are both from the same whale. And these are transverse sections, like through the vertebra this way, two CT scans of the same vertebra. So the neural spine is missing. This is the neural canal, the opening here for the spinal cord. And the white area here, all around, represents the dense compact bone, the lamellar bone, that would originally have been the outside of the vertebra. Okay? So after the trauma, this new bone grew here, 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 and here. All four sides have new bone growth on them. And when I first saw that, I was like, that's cool, but it didn't mean anything. I didn't understand the story behind it. I sent these images to an orthopedic surgeon, and he responded by saying, wow, that's amazing. What happened is that this trauma was so violent that the soft tissue that attaches to the sides and the bottom of the vertebra were actually ripped off the vertebra itself. The muscles and soft tissue were pulled away. And so this was an opening, the lumen, into which the animal bled. Okay, so it filled this area with blood, and then that turned to a hematoma and clotted. And then osteocytes, rapid response growth, bone growth filled in this space and grew this new bone to try to make the best of a really bad situation. So this was a hurting whale. From the maturity of the sizes of these bone growths, I'm not sure how long it would have lived. It would have been weeks to months that this whale would have survived. Until then, it finally died. And that we don't know why it died. So here's the tooth. It's not a terribly big tooth. It's not an impressive megalodon tooth. It's a rather teeny specimen. And we don't know if this tooth came to be associated with these vertebrae just because the megalodon was swimming along and it shed a tooth, and this tooth just sank to the bottom and happened to be preserved adjacent to these. Or if this is from the shark that was scavenging the dead whale carcass, or if it was from the shark that killed the whale after it had survived already one severe attack, or was it from the originating shark that created the trauma in the first place and was embedded in the body and stayed there until the whale died. That's a possibility too, but we can't tell. I don't know which one of those. So I know I've basically given it away, but we think that something like this probably happened. I think it's the most reasonable explanation for the severity of the trauma that's preserved in these bones, because I can't think of any other way that a baleen whale could so hyperflex its backbone so much. So we think that this whale was ambushed from below by a megalodon. And you'll see that the backbone of the whale is really bent. So a compression fracture or a spall fracture like this can happen to people who are in automobile accidents. And if they're only wearing their lower seatbelt, they don't have the chest belt on. And so when the impact happens, they're jerked violently forward. The backbone is bent so much that adjacent vertebrae apply intolerable strain on the bottom of the vertebra and break it away. In this case, it jammed it up into the back of the vertebra. So a really violent encounter. And I think the best explanation is megalodon. Although even though I have this tooth, I can't say for sure that it was a megalodon that did it. So we don't really have the smoking gun, but a lot of circumstantial evidence here. I just want to say a few words about competition. So what other organisms could have given megalodon a run for its money? The best candidate is actually this whale here, Leviathan. It's a late Miocene whale. And the skull was originally found in the Atacama Desert in Peru. And it's an enormous animal. And this is from that same film company. They included this in their documentary. What I'd like you to notice is how large the upper teeth are. Lower teeth are huge. In fact, you would say, well, that kind of characterizes even the modern sperm whale. They have large lower teeth. They only have little teeny, vestigial upper teeth. But this animal had huge teeth in both the upper and lower jaws. these sperm whales were probably not deep diving whales like modern sperm whale is. And they were probably feeding in the photic zone, and they were probably direct competition to Megalodon, feeding on marine mammals or even other large sharks. There may have even been encounters between this animal and Megalodon. Here's another great illustration showing the relative sizes of these large marine organisms. So while in Peru, I took this photograph of a large Megalodon tooth as compared to a Leviathan tooth. What's interesting about sharks is, as you know, they produce teeth and shed them throughout their life. Odontocetes, though, only get one set of teeth in their whole life. They don't even have milk teeth. The teeth that they're born with is the teeth that they die with if they don't wear them out. And so here's a single tooth. And so it's thought that these big sperm whales had to be very careful how they were feeding to not break their teeth. So in the same museum in Lima, Peru, there's this lovely restoration of the Leviathan, showing the massive jaws and huge teeth. And then in another view, just showing the wear facets, the occlusal facets, where the upper and lower teeth come together to help in the shearing of tissue. And finally, extinction. So I'm not going to dwell on this very long. So we don't know exactly why Megalodon became extinct. We think that, so the most recent paper that was published on Megalodon extinction calculated that they became extinct about 3.5 million years ago. And these are the 8 most common reasons that are given for Megalodon extinction. And there's so many, that's just because we don't know. We don't have a definitive answer to that. We don't have a meteorite from outer space that demolished their habitat or something really obvious that contributed to their extinction. So cooling climate, we know that the circum-equatorial currents were being disrupted and climate was cooling during the Pliocene when they became extinct. There's also extinction of some small baleen whales that may have been their principal source of food. So the range of Megalodon may have been fragmented. And as large predators, they're uncommon to begin with, right? They're not abundant because they're at the very top of the food chain. Faster swimming whales. I like this one here, the neonate megs susceptible to predation. So baby Megalodons may have been susceptible to predation by great whites or killer whales. Okay, so you don't have to necessarily kill off the adults. If you just get the babies, then you contribute to the extinction of Megalodon. There was even this suggestion that there was a supernova, and we know that there was, that bathed the Earth in high energy radiation, but it was 2.5 million years ago. So it's off by about 1 million years. So it doesn't seem to be like what killed Megalodon. And the reason for this is simply size. It simply has to do with the size of Megalodon. That its body would have been large enough to absorb a lot of this high energy radiation, contributing to a higher rate of tumors, cancers in that animal, and killed them that way. So the one that I like is the rise of killer whales. Now, apparently, at about 3.5 million years ago, killer whales were smaller than they are today, quite a bit smaller. And so it seems unlikely, but I like killer whales. Because they hunt in pods and they communicate with each other, and Megalodon would not have done that. It would have been solitary, probably solitary predators. And so I think these animals are the most amazing predators that kind of Earth has ever devised. Because like I said, they hunt in packs and pods and they communicate with each other to coordinate their attack, to kill their prey. Okay, end of talk. If you're ever in the Solomons area in the next year and a half, come to the Marine Museum because we have a newly opened exhibit on sharks. Sharks sink your teeth in, that's the title of the exhibit. And it features restorations of dentitions of fossil sharks from along Calvert cliffs, as well as jaws of sharks, modern sharks that are living in the Atlantic today. So we're comparing the Miocene fauna, shark fauna, to the Chondrichthian fauna that existed during the Miocene. This is actually a really nice restoration of the set of jaws of the ancestor of the living great white shark, which we have along the cliffs, Carcharodon hastalis. These are unserrated teeth. And just like the Megalodon lineage, Carcarcles, the living species of great white, evolved serrations, and we could track that evolutionary transformation in Peru right across the boundary from Miocene into the Pliocene. So as you know, I work at the Calvert Marine Museum, and we are actually a county facility. So 60% of our funding comes from the citizens and residents of Calvert County, for which I'm very grateful. And let's see, the artwork that you saw was done by Tim Shire and Shu Shoemaker, two really gifted artists. And I'm also very fortunate because I have an endowment to play with, the Clarissa and Lincoln Dryden Endowment, which funds basically most of all the salaries in our department except mine, and also the other any other expenses you might have. So I do have one more slide, or maybe a few more slides, depending on, but maybe we should stop there. Actually, no, I'm going to go on. I'm going to give you the one more slide. This might not be for everybody, but I grew up in essentially a fundamentalist, pretty strict evangelical Christian family home. And our answer to evolution and the age of the earth came from the Bible. Okay, so we took it selectively literally. So I believed in, growing up, I believed in a young earth, a young universe, 6,000 to 10,000 years old. And so obviously when I went to university, and even before that, but in university, I was challenged by, what I was hearing, because that wasn't what I had been taught as a child. And so needless to say, there was a lot of conflict on how to resolve that and maintain some semblance of Christianity in my life. And so my brother-in-law, Christopher Smith, had a similar sort of experience. And we came together on this when we spent a long time in a hospital because of my middle son. At birth, he had some issues. And so we were discussing this, and we came up with this book, which was published in, I think, 2005. It's no longer in print, but the contents are all online. And that's the website if you have an interest in reading our account that reconciles mostly, for me anyways, evolution and creation with retaining Christianity in my life. And it's free, so it's open to anybody. Do I have a few more minutes?
Well, I was gonna do.
We can do
questions.
Yeah, we can do questions.
Yeah. So what I was gonna say is, if you click right where stop share is, if you click here, here we go. I'll just you. So for folks that are on Zoom, if you have questions, you can feel free to go ahead and type them into the chat. And Chloe, if you want to unmute, you can read them out. And for folks in McLaughlin, if you all have questions, go ahead and raise your hands. And yeah, let's see what questions we have for Stephen.
Yes, go ahead.
And don't let Linda have all the fun.
Thank you for coming. That was awesome.
Oh, sure. Glad you enjoyed it.
It was
My
so
pleasure.
good.
Great.
Telling
Thank you.
good stories.
Thank you.
Just from looking at teeth, my goodness, it's great bones. I had a question about the teeth in particular. You were showing the bones and how they recalcified, had some CAT scan images, but I was wondering about the teeth themselves, kind of the innards of the teeth. And if I just had this thought and how they go about growing, because you're looking at the serrations of these teeth. And so that's an edge thing, but is it more deep within the tooth? Is it something that comes deeply within and is exemplified at the edge? Does that make sense, my question?
Yeah, so I'm not going to have a really good answer, but what I can say is that, sometimes you buy like chips or little like candies, and there's a little perforation, a little tear in the wrapping, so that's a weak point that you can pull it apart, okay, and open it up. So when sharks evolved serrations, each one of those little notches is actually a weak point along the tooth. And so in order for the serrations to survive and be effective, the sharks also had to evolve an osteodentine that would strengthen that area. And you can see that by micro-CT scanning, teeth that don't, teeth that do. There's a difference in the structure of the tooth that helps to fortify that area so that those serrations then don't become a liability to the shark.
So does that help you with the lineage? Is my comment.
Oh, I see, okay. I don't know, I've never thought about that. I know that when you CT scan, micro CT scan his teeth, you can see the pattern of vascularization inside the tooth. And so maybe that would be continuous along this sort of evolutionary lineage. Yeah, I don't know that. But that's a good question. Yes, yes.
Hey, now, why do you think that we haven't sort of had like a predator evolve into the niche of a predator for like modern larger whales that Megalodon was able to hunt?
Actually, Stephen, can you do us a favor? Can you repeat the questions when you get them for the folks on Zoom?
Okay, so why don't we have a macro predator? Why don't we have a macro predator that preys specifically on the large baleen whales? And I think the answer is that evolution is blind, as far as we know. And so it doesn't know what's going to evolve. And so maybe now, I mean, if we have millions of years to work with, maybe there would be a lineage of sharks or some other marine mammal, like killer whales. Well, actually, killer whales do prey upon large baleen whales. So that's the best, I mean, that's the best example because they actually do that. But so since evolution is blind, it can't respond like immediately.
There's often a lag.
That's right. And so it takes time for another group or organism to sort of be selected over a long period of time to develop the mechanisms and anatomy to be able to prey upon a large whale. But killer whales do. And in fact, killer whales, pods will often kill a whale and just eat the tongue and leave the rest of the carcass.
Whoa.
Yeah.
Seriously?
The tongue is a delicacy to
Oh my
them.
God.
And so they're just like, and they're like, they're ruthless. They're ruthless. I mean, I've seen these videos of like, poor like little baby whales.
No, okay.
Harass like the mother and the baby. And the pod of killer whales is, I mean, I can hardly watch it because it's like so like it's like this is really sad. But they harass the mother and baby until the mother gives up the baby and the baby is then consumed by the killer whales. But killer whales are very effective predators. Yeah.
So we need to think of them as super predators,
They're
even
super
if we don't
predators.
currently
Yeah.
think of them.
So there's one thing I didn't say that your question reminded me. When that otodus lineage, it started out with the unserrated tooth that was like the fork, and then it developed the serration, so it became like a knife. What that does is that allowed that from then on in that lineage, culminating in Megalodon, for those sharks to feed on animals that were too large to swallow whole. They could take a big animal, bigger animal than a fish, or an animal that's even larger than themselves, and cut out pieces very effectively. So that's what those teeth are really good at doing. They're good at cutting out pieces, smaller pieces, so you can eat the animal eventually, but you just have to take lots of bites. Yes.
In regard to the cuffs on the other side of the teeth of the older sharks,
Yes.
I was wondering about the purpose of those or the reason that Megalodon lost them.
Yeah. We don't actually
Can you
know.
restate again? Sorry.
Oh, sorry. So why are there cusplets at the base on the shoulders of the more ancient teeth in that lineage that gave rise to Megalodon? And why did Megalodon lose those cusplets? So we don't have a good answer for that, but it's been suggested that those little cusplets help to fill the space between adjacent teeth, okay? So that food would not become lodged or wedged between two adjacent teeth. So it had a functional purpose, okay? It wasn't just decorative or a holdover from, I mean, most ancient sharks do have that little cusplet on the side, but it was lost. So when that lineage of sharks, the Otodontidae, developed the serrations, then you don't want anything in the way of those serrations. You don't want something blocking it. You want the tissue to be forced down into that wedge along that cutting edge, and then eventually just like, you don't want to have a little cusp there to stop the tissue. You want it to go like right through. So you want like a smooth cut. And that would be my answer, but I don't know that's what was driving it. So when you get such a tiny little vestigial, what's puzzling me is you get such a tiny little vestigial cusp. How can like natural selection reach in and like continue to like select against that feature? How can it finally get rid of it? But it got rid of it. And I don't understand that. If someone has an answer to that, I'd love to know why or how. Maybe it was just like the timing in the development, like something to do with like Hawks genes or something, or a sonic hedgehog or something that just changed when in the ontogeny, in the development of the tooth, that little couplet was lost. Yes.
I was wondering if it looked like the kind of like predecessors to the megalodon, the teeth were getting a little bit larger each time. I was wondering what the like limiting factor on megalodon growth was and why they didn't just kind of keep growing into the movie sharks.
Oh, I've never thought of that. So why did they only like grow up to like 66 feet long and not like up to
They could have
100?
gone to like 120.
Yeah, yeah. I have no idea. I've never thought about that. I've always thought, like this is the limit, and I didn't think outside the box. Like what was limiting? I don't know. I have no idea.
Maybe not having enough food. So, I mean, something even bigger would require a huge amount of food to be able to keep going. Could it be surface area to volume issues? Like where they're living in the
It
oceans?
could have been that. We know that, we think that Megalodon was mesothermic, which means that it didn't warm its body equally everywhere like we do, but it was like great white sharks, because they're both lamniform sharks. They're different families, Lamnidae and Otodontidae, but they're still lamniform sharks. And most of them have that ability where they're mesothermic. So they can warm just certain critical parts of their brains, their vital organs, their muscles, and so they can think faster, they can respond more quickly. Where am I going with this? I don't know.
So when you're really, really big, it might be very
So
difficult.
because you're mesothermic, your metabolic rate is higher, and you do have to like consume. I think they have to consume like a cow every day, like that much food. And so that may have been the limiting factor on the size of Megalodon and that lineage. But
I bet we could test that.
so here's the other thing to think about. So maybe they were only limited by the fact that they became extinct. And we don't know exactly why they became extinct. Perhaps it was all of those factors that I showed you. It was extinction by 1,000 cuts, right? Each one of those maybe contributed a small part to fragmenting their habitat, their range. And once you did that, then there's a good reason for them to become extinct. But if they hadn't become extinct, maybe they would have continued to increase in size, because that whole lineage, starting with 60 million years ago, the Ototus obliquus, there's an increase in the size of the sharks at each stage along that chronospecies, where one species evolves gradually into another.
Chloe, do you want to read out the question from Zoom?
Sure. So Orion asks, do shark teeth differ from other animal teeth? Can we see any evidence of their composition through the fossil record?
Yeah, so do shark teeth differ from other animal teeth? Can you see any evidence of their composition throughout the fossil record?
Yes. Shark teeth, even though they have an enamel coating on them, it's a little bit different than chemically than the enamel that covers our teeth. And it's characteristic of sharks. And the closest thing to bone in a shark's skeleton is the root of the tooth. That's what comes closest in terms of its composition and structure to bone.
Orion's wondering if they can come in at 5 o'clock to see some of the samples.
Oh, sure.
There we go.
I'll be happy to stay. Yes.
So, your vertebrae that you held up, maybe it's because I'm all the way back here and it was dark. If you're out in the field just walking around and you stumble on that, how do you know that that's a bone that's been preyed upon versus just something that's been broken because it's 20 million years old? I'm so excited right now.
So you can hold it. So when you are out along Calvert Cliffs, if the fossil is in situ, right in the bed, if you're not an experienced collector, you might not even see it at all, because the sediment is no staining it, and it's much the color of the original sediment. So these two vertebrae were actually found in place. They hadn't eroded from the cliff face and had just tumbled onto the beach. But even if they had, we would still know that they're fossilized because of their morphology. They're unlike anything that's living in the bay or in the Atlantic Ocean today. And because they've been permineralized, right? They're heavy. They have rock-forming minerals that have been added to the bone. So the original fossil bone, the original bone is still there. It's just that all that spongy interior of bone, much of it is infilled with rock-forming minerals. And then, so because we CT scanned it, we could clearly see what was happening inside the bone to the bone. And you can clearly see that's been broken away. So that break is not something that happened when the vertebra fell out of the cliff onto the beach, if that's what happened, but in this case it didn't happen. And we can see that there's that new bone growth that grew after the trauma to sort of try to keep the vertebra together and continue making it functional so the whale could live. But eventually, and not long after the injury, the whale died. So did it die of another predatory attack by Megalodon? Was it weakened? Was it like starving? Yeah, so did it maybe have like septic infection that like spread through its body and killed it that way with sepsis? We don't know.
Thank you.
Yeah, sure.
Other questions for Dr. Godfrey? Elizabeth?
Yes.
So if it was alive today, like in the movie, how sustainable would it be? Because consider the food source would be perhaps like a lot better since you have bigger whales.
So in terms of where Megalodon teeth are found on Earth, they're not found north of the 55th latitude. Okay, so Megalodon seemingly was not able to tolerate cold water. And a lot of baleen whales that live today, I don't know if it's like ubiquitous or for all of them, they migrate though to the upper parts of the Northern Hemisphere, to the Arctic to feed. And so actually that's one of the suggestions that was made as to why Megalodon became extinct, because whales started to migrate and whales migrated and Megalodon couldn't follow them into the cold water. So Megalodon would have to find prey that would stay within its habitat, that would stay in lower latitude areas. And I think it probably could do that. I mean, Megalodon would feed on anything that it could catch. There would be nothing that would limit it in terms of like size today. If it was living today, it would definitely be able to feed on the largest baleen whales.
And not humans, right? Because I think modern sharks don't do that either because they just, I guess, don't tolerate our meat. But
I don't think it has anything to do with our meat. I think it has more to do with our bones. Apparently, great white sharks like try to avoid biting bone because even though the teeth are super sharp, they don't have the teeth in the great white are not really firmly held to the jaws. When you look at the shape of the root of the tooth, it doesn't have the long handlebars that act as, well, like in handlebars, to give good mechanical advantage to the Sharpie fibers that are holding that tooth to the jaw. But what happens is when a great white bites, the tooth moves, and there's actually kind of a recoil to the tooth, which helps to cut it. So they're really good at cutting. But apparently, great whites will avoid biting the parts of animals where there's lots of bone because they don't want their teeth to impact and strike the bones because they could then fall out. And so since we're so bony, plus, Megalodon would have no interest in us. We would just be swallowed.
We're not much of a payoff, really.
Yeah.
Probably not worth the effort.
Yeah. Yes.
So if you were to, like, hypothetically, if you could find like one bone or fossil from a Megalodon, what would give you the most information? Like what body part or what fossil would give you the most information about their like behavior?
So the best thing would be to find the chondral cranium. Chondro just means cartilaginous, cranium, the front part of the skull. So sometimes in sharks, we find the very tip of the rostrum that's fossilized, but that's all. We haven't found any other part of a Megalodon body other than the vertebrae, which are areolar tissues. So they have a higher mineral content, and so that's why they're sometimes preserved. There's a specimen in Belgium which preserves a good part of the backbone of Megalodon, but I don't think there are any teeth associated with it. So they can't compare like the size of the teeth to the size of the vertebrae. So there's still a lot of conjecture in terms of like the details of the cartilaginous skeletal morphology of Megalodon. having the chondrocranium, because it's such a complex bone and lots of things are happening in there, organs and muscles attaching to it, and nerves, that would give you the most amount of information in terms of who it's most closely related to in terms of the modern sharks, and what that shark looked like in terms of the details of its anatomy at that time.
How about one more question, Olivia?
Oh, wait, I don't know if you did it on mine, but I was just gonna say, okay, blue whales, are they still significantly bigger than Megalodon?
Yes.
Okay.
Yeah, so a female southern great blue whale can be over 100 feet long. In fact, if you are ever able to go to the Smithsonian's Garver facility, which is in Silver Hill, Maryland, it's just off of the Beltway along Suitland Parkway. They have giant warehouses filled with like the national collection. So if you go like downtown to the museum itself, Natural History Museum, there's only a small part of the collection actually housed in the museum. They have these warehouses outside of DC housing the collection. And there are two buildings that house the world's largest collection of modern whale and dolphin skeletons. And they're just enormous. Well, in this collection, there's two bones, and they're the two largest bones known anywhere on Earth. They're 26 feet long. So that would be like from me to that wall over there. And they're the lower jaws of a southern female great blue whale that was picked up on like South Georgia Island or something from a whaling station when great blue whales got to be that size. So they're, and in cross section, like the bone is like this big around in section. It's just like mind boggling how big those blue whales get to be.
All right, so I'm sure Dr. Godfrey wouldn't mind sticking around if folks have other questions or they want to come up and see the vertebrae or the tooth. But in the meantime, let's thank you very much for joining us today.